Okay, so in this video, we're going to take a look at some of the factors that can affect the rate of a chemical reaction. And remember from the last video, and it was said right at the end, that the rate of a reaction is also the same as saying the number of successful collisions per unit time. Okay, and this idea is going to be really important when we start to give reason to our factors that can affect the rate of reaction. So let's start off with one of our factors, and our first factor is going to be temperature. So let's see how temperature can affect the rate of a chemical reaction. Well, an increase in temperature, so if we increase the temperature, we're going to increase the average kinetic energy of our reactant particles. Okay, so you add temperature or you increase the temperature, our reactant particles are going to move around the reacting vessel a lot faster. This therefore will increase the proportion of reacting particles that have a kinetic energy which is sufficient enough to overcome the activation energy. Okay, which therefore increases the probability of a successful collision, which increases the number of successful collisions. And an increase in the number of successful collisions means we're increasing the reaction rate. So if we increase the temperature, we're going to increase the reaction rate. And let's see what that looks like on a Maxwell-Boltzmann curve. So this is going to be my Maxwell-Boltzmann curve here. And remember, on a Maxwell-Boltzmann curve, we have the kinetic energy of the particles, and then we have the number of particles with that kinetic energy. Okay, and it looks something like this, remembering from the last video. And we have our activation energy sitting about here somewhere. So that's our activation energy. So at the moment, we have all of these particles here with sufficient kinetic energy to overcome the activation energy. However, when we increase the temperature, so in green, for example, we increase the temperature, what we do is we shift our curve this way a little bit. And I'm going to extend our axis just along there like that to make it a little bit longer. So what we have now is we have a greater proportion of reacting particles with sufficient energy to overcome the activation energy. So here's our activation energy here, remember? But now we've got all of these reactant particles that have sufficient energy, kinetic energy, to overcome the activation energy, because we have more particles traveling at a greater kinetic energy. So let's have a look at one more. Say we increase the temperature even further. It's going to distort this graph or this curve even more. We now have an even greater proportion of particles that have enough kinetic energy to overcome the activation energy. We now have all of these as well as what's in the green and the blue there. Okay, so that's how temperature change can be demonstrated on a Maxwell-Boltzmann curve. And here it should be important to note that we have temperature 1 in blue is less than temperature 2 in green, which is less than temperature 3 in purple. Okay, so that's how temperature can affect reaction rate. Let's have a look at another example. So this time we're going to have a look at how pressure can affect reaction rate. So what happens if we increase the pressure of our reactant vessel? Well, if we increase the pressure, we're going to decrease the distance between our reacting particles. Okay, so for example, we have our reactant vessel here, and we have our particles, our reactant particles here labeled R. And then we decrease the volume, for example. So we decrease the volume of this container, and now we have R's are all much closer together. Okay, so by decreasing the volume or increasing the pressure, we're going to decrease the distance between our reacting molecules. This in turn will increase the number of times that they collide. Okay, that doesn't necessarily mean that we're not necessarily meaning the number of successful collisions. We increase the amount of times these guys collide, which therefore increases the number of successful collisions. Okay, so we've got to be really careful with the way that we word these steps. Increases the number of successful collisions, and we know that if that occurs, we're increasing the reaction rate. So increases in pressure increase the rate of our reaction. Let's have a look at another property. Let's have a look at surface area. So surface area, and it's a lot of the time abbreviated to SA. So what happens if we increase the surface area, and what do we mean by this? So let's take a look. Here we have our reactant molecule, and we've got these two reactant molecules here as big cubes. Okay, and all of our particles, our reactant particles, are all inside. Okay, so these are all individual reactant particles that could undergo a chemical reaction. So we've got all of these inside. Well, at the moment, we've got a lot of these reactant particles that are hiding, and they're not going to collide with each other. But what if we chop this cube up into tiny little pieces? So we're going to chop this cube here up into little cubes. Okay, so we chop it up into little cubes. I'm going to draw my cubes out. We now have a lot more particles that are available to react with the other reacting molecule. Okay, so if we increase the surface area, in other words, if we finally chop it up, so in other words, finally chop it up, or a lot of the time put it into a powder or granules. Okay, if we increase that surface area, we are going to increase the number of reacting particles available for collision. If we increase the number of reacting particles that are available for collision, then we are going to increase the number of collisions. And if we increase the number of collisions, we're going to increase the number of successful collisions. And we know that that in turn increases our reaction rate. So if we increase the surface area, in other words, we finally chop up our reactant particles, okay, into tiny little pieces, or we put them in powders or granules, okay? So for example, we have, say, some zinc metal or something here. So this is zinc metal, but we're going to chop our zinc metal up, or it might be magnesium strips, or whatever it is, into tiny little pieces. We've got 1 here versus 5 here. That's essentially the crux of the surface area property. Now, let's have a look at what happens if we use a catalyst. So this is another method. We might put a catalyst in. Now, a catalyst, its role is to decrease the activation energy. Okay, so what does that look like on a Maxwell-Boltzmann curve? Well, let's have our Maxwell-Boltzmann curve here, okay, and we're going to have our number of particles on the y-axis, and we're going to have our kinetic energy on the x-axis here, and our Maxwell-Boltzmann curve looks something like this. Okay, and again, I'll just extend out our x-axis a little bit, and we have our activation energy sat here normally. And we have all of these particles here that have sufficient kinetic energy to overcome the activation energy. However, what happens if we add a catalyst? We lower the activation energy. So the activation energy comes back to here somewhere. So this is activation energy with a catalyst. So we now have all of these particles as well with kinetic energy able to overcome the activation energy. So if we lower the activation energy, we increase the proportion of reactant particles with kinetic energy bigger than the activation energy. This therefore increases the probability of a successful collision, which increases the number of successful collisions. And hence, will increase the reaction rate. Okay, so that's looking at a catalyst. And there's one more that I want to look at, which is concentration. So let's say that we increase the concentration. Okay, so for example, we have our reacting vessel here. This is reacting vessel 1, and this is reacting vessel 2. Okay, and it's an aqueous solution, so that's our aqueous level there. It might be water that it's in. Okay, and we have all of these aqueous species. So reactants, 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 reactants. So there's, say, 6 there. But here, we put 12. Okay, so there's a lot more reactant molecules in here than there are in here. So there's going to be a lot more collisions occurring in the more concentrated reacting vessel. So if we increase the concentration, we increase the number of particles, okay, or reacting particles, which increases the number of collisions. And again, if we increase the number of collisions, we're going to increase the number of successful collisions, which increases our reaction rate. Okay, so finally, increasing concentration increases reaction rate.